Okay, so 1 through 3 want us to write as a sum and or difference of logarithms. And so what they want us to do is take this single log and break it apart into multiple logs. So we have a log base of 13, that doesn't matter. What's happening between the 21 and the 5 is division, which means that when I break it apart and write it as 2 logs, I'm going to be subtracting them. So log base 13 of 21 over 5 is equivalent to log base 13 of 21 minus log base 13 of 5. And that's your answer. Done. Number 2 has 1, 2, 3 pieces. We have multiplication happening here and division happening here. And so we're going to have 3 logs and we're done. This is log base 3 of 2. Multiplication means I add the logs, so plus log base 3 of the square root of r minus log base 3 of s. And then you will remember that the square root of r can be written r to the 1/2 power. And that if we write it like that, that exponent inside a log can come down to the front. So this is actually log base 3 of 2 plus 1/2 log base 3 of r minus log base 3 of s. And that's your answer for that one. Okay, and then number 3 with the natural logs. Again, we have 1, 2, 3 pieces. We're going to break those apart. And then after we break it apart into 3 logs, then we're going to deal with exponents. So this is the natural log of 2 plus the natural log of u cubed plus the natural log of v to the 5th. And now it's in 3 logs, which is what we want. We pull down the exponents to the front. And you have to do that at the end because the cubed only applies to the u and the 5th only applies to the v. And so we have to wait until we've broken it apart into separate logs before we pull the exponents down. This is ln of 2 plus 3 ln of u plus 5 ln of v. And that is your answer. All right, 4 through 6 wants you to put logs back together. So when we're taking them apart, we break them apart based on multiplication or division, then deal with the exponents. When you're putting logs together, you deal with the exponents first. And so right here I've got a 5 and here I've got a 6, and I put those numbers back first. So this is log base b of m to the 5th minus log base b of n to the 6th power. And now that the exponents are back, I can put these together because there's subtraction there. That means division when I put it together as one log. This is log base b of m to the 5th over n to the 6th, like that. Again, with this one, we have to first put our exponents back. So I've got log base 4 of p squared plus log base 4 of q cubed. And we put the exponents back, and then we put together the logs. Because we are adding here, that means we are going to multiply the logs. So this is log base 4 of p squared q cubed. All right, last one. Again, first thing you do is put your exponents back. That 1/2 goes on the r, the 5 goes on the s. So this is the natural log of r to the 1/2 plus the natural log of s to the 5th. And then we're going to put those two things together. You can write r to the 1/2 as the square root of r, and so we should probably do that. This is the natural log of the square root of r plus the natural log of s to the 5th power. We put them together using multiplication because of that plus sign right there. This is the natural log of, I would write s to the 5th square root of r, because you put your root term last so that you don't accidentally put something that's not a root under the root. All right, guys, 7 through 11 have you solving for x, and so we're going to solve exponential equations using logs and solve log equations using exponents. The first 3 equations are exponential equations. You get the thing with the exponent alone. So in this case, the thing with the exponent is e. I need to get it alone, and I do that by dividing both sides by 7. And so I get e to the 3x is equal to 7. 49 divided by 7 is 7. And then you take the log of both sides with the base of whatever this number right here is. This is my base on my exponential term. I take the log with that base. So it's a base of e, which means it's a natural log. So ln of e to the 3x is equal to ln of 7. And what happens over here is that ln of e cancels out, and we just get 3x is equal to the natural log of 7. And from there, you can just solve the equation. So 3x is equal to ln of 7, divide by 3. You get x is equal to the natural log of 7 divided by 3. Oh my goodness. And that's 0.648. For number 8, again, the first thing we do is get the thing with the exponent alone, and in this case that's a 5, and it is alone, so I don't need to worry about that. And so the next thing we do is take the log of both sides with this base right here. So this is log base 5 of 5 to the x squared plus 1 is equal to log base 5 of 625. What happens when we take the log base 5 of 5 to the x squared plus 1 power is that it just becomes x squared plus 1. Log base 5 of 625 is 4. This is a quadratic equation, but we can solve that. We just subtract 1 from both sides. And then take the square root of both sides. And so your answer is x equals positive or negative root 3. All right, guys, number 9 as well, get the thing with the exponent alone. In this case, it's a 7. And so I don't have to do anything to get that alone. What we're going to do is take the log with that base right there of both sides. So this is log base 7 of 7 to the negative 2x is equal to log base 7 of 4.5. This becomes negative 2x is equal to log base 7 of 4.5. And then you just solve for x, so I divide both sides by negative 2. I get x is equal to negative 0.38647. That's your x value. All right, for 10 and 11, we are solving log equations, so we're going to have to use exponents to do that. And so the first thing you want to do is make sure the logs are completely alone. I've got a 2 here and a 5 here. How do I make sure the logs are completely alone? The answer is that you put those the 2 and the 5 back up on the terms inside the log as exponents. So this is log base 5 of x squared is equal to log base 5 of 6 to the 5th power. You don't have to know 6 to the 5th power. We have a calculator for that. And now that the things with the logs are completely alone, we raise both sides to the base power. So this is log base 5. I'm going to make those both exponents on 5. And so I get x squared is equal to 6 to the 5th power. That's x squared is equal to 7,776. To solve for x, you take the square root of both sides. X is equal to plus or minus 88.1816. Now, it is important to remember that we have restrictions on what values can be inside of a log. And so there was an x inside this log. That means that my x value had to be bigger than 0. I needed x to be greater than 0. Our solution is positive or negative 88.1816. Well, x has to be bigger than 0 because we can't take the log of a negative number. And that means that my solution for this is only the positive 88.1816. The negative 88 is not a solution to this equation. Only the positive. All right, guys. Looking at number 11, we can look at like our domain restrictions or restrictions on solutions first. So if I have x plus 2 inside the log, that x plus 2 has to remain bigger than 0. I can't take the log of a negative number. And if x plus 2 has to be bigger than 0, that means x has to be greater than negative 2. And you guys should remember that we did that when we solved log equations. We found our restrictions on solutions first. So x must be bigger than negative 2. Now that we have established that x has to be bigger than negative 2, we're just going to solve the equation. I have 2 logs here. What we need to do, guys, is we need to put these 2 logs together and then get rid of them. So this 3 needs to go back up there on the x plus 2, and then we're going to divide. So this is log base 2 of x plus 2 cubed minus log base 2 of 8 is equal to 3. And then this minus here means division. So this is log base 2 of x plus 2 cubed over 8 is equal to 3. And then what we do is we make both sides of the equation a power of 2, and that's because of the 2 right there. This is x plus 2 cubed over 8 is equal to 2 cubed. So that's x plus 2 cubed over 8 is equal to 2 cubed is 8. To solve, we multiply both sides by 8. So we get x plus 2 cubed is equal to 64. You take the cube root of both sides. You get x plus 2 is equal to the cubed root of 64 is 4. And then you can solve for x. So you subtract 2. X is equal to 2. And that's our answer. We come back up here and we remind ourselves that at the beginning we said x had to be greater than negative 2. Positive 2 is greater than negative 2. And so that's my answer. right, guys. Now we're in the applications problems, which is what we've been doing for the last couple of weeks. Number 12 says if $10,000 is invested for 3 years at 4% compounded continuously, what is the future value? So remember that compounded continuously, that's this function, A equals PE to the RT, where A is our final value, P is our principal, that's how much we put in, R is the rate, and T is time. They gave us most of these. They told us we put $10,000 in the account. They told us the rate is 4%, which we write as 0.04, and they told us we're going to leave the money in the account for 3 years. So they just want the A value. So A equals 10,000 E to the 0.04 times 3. So you just throw that into the calculator and you get 11,275. Okay, and then number 13 is using compound interest but not continuously compounded. So the equation they're using is A equals P to the 1 plus R over N to the NT, where A is the final amount, P is the principal, R is the interest rate, N is the number of times it's compounded a year, and T is your time. And so they told us most of this. They told us the principal is 5,000. They told us the interest rate is 8%, so it's 0.08. They told us it's compounded quarterly, so N is 4 times a year. And they told us that we're going to leave it in the account for 5 years. And again, all you're asked to do here is plug all of these numbers into this formula. So A equals 5,000 times 1 plus 0.08 over 4 to the 4 times 5 power. And that gives you $7,429.74. All right, guys. 14 says find the present value and round to the nearest cent to get $10,000 after 6 years at 11% compounded monthly. So we want $10,000 after 6 years at 11% interest compounded monthly. So what we want is the p-value, the principal. And so this is that same equation we were using for 13. A equals p 1 plus r over n raised to the nt power. And they've given us everything but p. And so the way we find p is that we divide a by this amount right here. And you can do it now or we can do it after we plug in numbers. We're going to plug in numbers first. So they gave me a of 10,000. We know our interest rate is 11%, so it's 0.11. And we know it's compounded monthly, so my n is 12 times a year. And that they told us the time was 6 years. And so we just plug in those numbers and then we're going to divide by this value. So 10,000 is equal to p times 1 plus 0.11 over 12 to the 12 times 6 power. And we're just going to divide by this thing right here. So this is 1 plus 0.11 over 12 to the 12 times 6 power. That's a times, not a point. We divide both sides. And that gives you P. So P equals, and then what we do is we plug this piece into the calculator. So 10,000 divided by 1 plus 0.11 divided by 12, all raised to the 12 times 6. And when you do that, you get $5,184.08. So that's how much money we would have to put into the account in order for us to have our investment grow to $10,000 after 6 years at 11% interest compounded monthly. All right, 15 wants to know how long it's going to take for an investment to double in value if it earns 4.5% interest compounded continuously. So that's again A equals PE to the RT. That's that formula right there. What they've given us, we know that the interest rate is 4.5, so 0.045. And they didn't give us any other information, but that's okay, because I know that the time or the amount I'm looking for, I want my investment to double. So the amount I want in the end is 2 times P. I want my investment to double. And so this is 2P is equal to PE to the RT. My final amount should be twice as much as I put in. And when we set it up like this, we can see that I can just divide both sides by P. I can get rid of that principal amount because that doesn't matter. And so 2 is equal to E to the RT. And now 2 is a number, E is a number, R I have, and I can solve for T. And that's what they want us to do. So this is 2 is equal to E to the 0.045 T. And the way we solve this is we take the log with the base that is the same as the base of our exponential term. And in this case, it's an E. So this is the natural log of 2 is equal to the natural log of E to the 0.045 T. And what happens is that this stuff cancels out and we just get 0.045 T is equal to the natural log of 2. And so we solve for T by dividing by 0.045. This is natural log of 2 divided by 0.045. And when you do that, you get T equals 15.4033. So about 15 and a half years is how long it's going to take your investment to double at 4.5% interest compounded continuously. All right, number 16 is talking about bacteria. A colony of bacteria grows according to the formula N of T equals 120 e to the 0.045 T, where N is measured in grams and T is measured in days since last Monday. Last Monday was April 16th. What date will the population reach 250 grams? So I'm looking for time, and then I need to remember that they want me to give them a date, not just a numeric value of 5 days or 7 days, right? They want a date. So, but I'm looking for time. So they want to know what date will the population reach 250 grams. That's my N of T. That's my final amount, right? My population at time T is 250. And I want to know what that time is. And so what we do is we set that 250 equal to 120 e to the 0.045 T. And we do this like we do all of these problems. Divide by the thing in front of the exponential term, so divide by 120. All right, and you get 2.5. You get 25 over 12. We'll just leave it at that. E to the 0.045 T. And then we're going to now take the natural log of both sides. And this cancels out, we just get 0.045 t is equal to the natural log of 25 over 12. And we divide by 0.045. So t is equal to the natural log of 25/12 divided by 0.045. And that is 16.3104. Now, that's how many days since last Monday it took for the population to reach 250 grams. They want an actual date, though. So if last Monday was April 16th, 16 days past April 16th, that's May 2nd. May 2nd. So it's May 2nd. Because April's a 30-day month. All right, guys. 17, a 64-gram sample of germanium 66 is left undisturbed for a certain number of hours. Germanium 66 decays at a constant rate of 27.7% per year. Therefore, the equation for the amount P of germanium 66 remaining after T hours is this equation right here. This is the same equation we've been using the whole time. It just, it just has a negative exponent now. How many hours will it take to only have 2 grams of germanium 66 remaining? So they want a time, and they told us we know our final amount is 2 grams. So what did they give us? They gave us our original amount, which is 64, and they gave us how much we have left in the end. They want to know, if we start with 64, how long is it going to take us to get to 2? And so you plug these numbers in here and here. So 2 is equal to 64 e to the negative 2.77t. We solved this equation exactly as we solved the equation above. So divide by the number in front of the exponential term. This is 1 over 32 is equal to e to the negative 2.77t. And now that my e term is alone, I take the natural log of both sides. This is the natural log of 1 over 32 is equal to the natural log of e to the negative 2.77t. This cancels out. I get negative 2.77t is equal to the natural log of 1 over 32. Divide by negative 2.77. And I get t is equal to 1.2511. So they said it decays at a constant rate of 27.7% per year. And then they want to know how many hours. I'm going to go with this was a typo, and we're going to call this years.
You did like 2.77 or 0.207.
Thank you, guys. Sigh. What did we get if we did 0.277?
Yeah, 12.51.
Okay. Well, yeah, because it's just one decimal place over. 5117. Okay, but we're still talking about per year, and it asks for hours, and we're gonna just say it's asking for years, because we're not gonna do a useless conversion like that. All right, guys.
All right, miss.
Number 18. Next time, stop me at the beginning, guys. All right. A sodium isotope has a half-life of 15 hours. Determine the amount of sodium that remains from a 4-gram sample after 45 hours. So if our half-life is 15 hours, right, and that we're using the same equation. So if we're talking about half-life, our final amount is 1/2 the initial amount. Okay, and we know that that final amount happens at 15 hours. So that's initial amount e to the 15 times the rate at which we lose the sodium isotope. And so what we do is we set these two things equal. So this is 1/2 p sub 0 is equal to p sub 0 e to the 15r. And we're looking for that rate at which, we called it k on the worksheet, but it's the rate at which we're losing the isotope. So this is 1/2 is equal to e to the 15r. Take the natural log of both sides. So the natural log of 1/2 is equal to 15r. This simplifies just to the 15r. And then you divide by 15. So r is equal to the natural log of 1/2 divided by 15. And that is negative 0.04621. And so that's our R value. We've now found our specific equation for this isotope. So my final amount is equal to my initial amount, e to the negative 0.04621 t. And we want to determine the amount of sodium that remains from a 4-gram sample after 45 hours. And so my initial amount is 4, and my time is 45 hours. And so we just plug the 4 and the 45 into this equation. So P is equal to 4 grams times e to the negative 0.04621 times 45, like that. And you get 0.499996 grams. Okay. All right, guys, last problem. Given that the half-life of carbon-14 is 5,730 years, consider a sample of fossilized wood that, when alive, would have contained 24 grams of carbon-14. It now contains 1.5 grams of carbon-14. How old is the sample? We want a time on this. And in order to find the time, we have to find our multiplication factor. So we know that our amount of carbon-14 at 5,730 is equal to half of the original amount. We know that. And we know that the amount of carbon-14 at 5,730 years is equal to my original amount times e to the rate at which it decays or decomposes or goes away times the time of 5,730. And so what we do is we take these two things and we set them equal. And then we solve for r. So 1/2 p sub 0 is equal to p sub 0 e to the 5,730 r. And my p's cancel out, and I get 1/2 is equal to e to the 5,730r. And we take the natural log of both sides, and if this feels familiar, it's because we did it right here with just a different multiplier, right? So this is 5,730r. The natural log of 1/2 is equal to 5,730r. And to solve for r, we divide by 5,730. When we do that, we get r is equal to negative 0.000121. So that's the rate at which we're decaying. And so my final amount is equal to my initial amount times e to the negative 0.000121 t. They want to know time. It started with 24 grams. We ended with 1.5 grams. They want to know how long that took. So 1.5 is equal to 24 e to the negative 0.000121 t. Divide by 24. We're going to get another piece of paper because we are running out of space. And so you get 1.5 over 24 is equal to e to the negative 0.000121 t. Take the natural log of both sides. When you take the natural log of this side, this just comes down, so it's negative 0.000121 t is equal to the natural log of 1.5 over 24. To solve for t, divide by negative 0.000121. We get t is equal to $22,914 years. So that sample of wood is almost 23,000 years old.